ciclo Seminários Internacionais em Materiais Compósitos, um evento promovido pela Regional Sul da ABPOL, que tem o apoio da ABPOL sede e também conta com o apoio da MTS Sistemas do Brasil, Texiglass e Instituto Senai de Inovação em Tecnologia de Polímeros. Né? Então, lembrando que esse é o nosso 5º seminário. Para o pessoal que está esperando o certificado, vale lembrar que a partir do 4º seminário, ao invés do 5º, nós vamos fornecer o seminário para vocês. Tá? Nós temos ali o controle da lista de presença e a gente vai cruzar os dados e depois enviar os certificados para vocês. Podem ficar tranquilos. Tá? Bom, lembrando que vocês não devem se esquecer de colocar aí no chat o nome e a instituição de vocês, a lista de presença. E se vocês tiverem dúvidas, vocês podem acessar o Mentimeter lá e colocar a dúvida de vocês. O nosso seminário de hoje ele é oferecido pelo professor Erik, lá da Universidade de Delaware. Hello, Erik. You listen me?
Erik is further. No, he's there. I can see his eyes moving. Erik. Yeah.
Okay.
Hey.
Hello. Professor Erik, thank you very much for accepting our invitation. In my name, in the name of ABPOL Sul, it's a pleasure to receive you today to speak about this topic. Thank you very much. Now I will pass the word to the chairman, the great chairman, Professor Sandro. Is with you.
Okay, thank you, André. So my role here is to introduce our guest and to mediate this talk. Okay, so I'm going to introduce you to Professor Erik Thostenson. Professor Erik Thostenson is currently Associate Professor in the Department of Mechanical Engineering at the University of Delaware and holds a joint appointment in the Department of Material Science and Engineering. And he is affiliated faculty of the University of Delaware Center for Composite Materials. And also president and co-founder of MCET Technologies. Professor Thostenson's research focuses on processing and characterization of composite materials, focusing on carbon nanotubes and advanced fiber reinforcements towards the development of novel multifunctional composites. His research in composite materials is widely cited in the scientific literature, more than 18,000 citations. So this is Professor Erik Thostenson. Erik, it's a pleasure to have you here. Thank you again for having accepted our invitation. And I invite you to start your talk, and I will ask you questions if they come in the meantime as we agreed. Thank you, Erik. Please feel free to start. Thank you.
Thank you for that very kind introduction. It's my pleasure to be able to talk to you today about some of our work. Over almost 20 years now, I've been fortunate to work in the field of nanostructured materials and composites, and specifically what I'd like to talk today about is how do we use nanostructures to modify the functionality of traditional fiber composites. Specifically, my work is in carbon nanotubes, but I think this is broadly applicable excuse me, to a lot of other nanostructured materials. So, and specifically, I'd like to talk about a couple of the case studies in specific applications that have been enabled by some of our fundamental research over the years in both processing as well as characterization, and now taking this to the next level where we can use these for applications in structural health monitoring, and most recently, it's been a very fun area to work in, is in smart garments. So just a little bit about where I'm from. So a lot of people, even in the United States, kind of forget where Delaware is because we're small, but we're very centrally located on the East Coast, really just between New York and Washington, D.C., and we're very close to Philadelphia in Baltimore. And on the Newark campus, this is what our campus, this is the main engineering building, and this is what it looks at this time of the year. Normally, I'd invite everyone if you're here to visit, but most of the buildings are closed right now. But Delaware also, very recently, is the home to the President-elect of the United States. He's a University of Delaware graduate and also a colleague. He has a faculty appointment at the university as part of the Biden Institute for Public Policy. So with that, I guess I would just also want to mention, as Sandro mentioned, I'm affiliated with the Center for Composite Materials. It's the oldest research center here on campus and has really been an interdisciplinary center of excellence in composites education and research. And it spans everything from fundamental research now to transition in technology to industry. And I think also, mark the date. Hopefully everyone will be able to travel by 2023. I am co-chair of the ICCM 24 conference, and that is being held in Baltimore, just about an hour down the road here from Newark. And I'm currently in the Center for Composite Materials right now. Okay, so just a brief outline. I'll give a brief introduction, talk a little bit about multifunctionality and how we can use nanostructures to modify the functional properties of composites, specifically the applications, and in my research is in sensing, but I think multifunctionality encompasses a very broad range. Then the next two items I would like to talk about is some of the background research we've done over the past several years, specifically the manufacturing approaches that we can use to produce this material. And I think this is really the enabling technology that allows us to explore some of these unique applications. And then our initial work was in utilizing these nanocarbon networks to sense damage in situ. And it's a very powerful technique for that. And we've taken it really from the laboratory now into applications. And then the next two is really the heart of the presentation, is utilizing these composites for structural health monitoring. And I'll talk about a specific application where we have these on a bridge in Wilmington, Delaware. And then also utilizing these unique composites for smart garments. So again, I think, just multifunctionality, and then, I talk about this, and my lab is named here at the university, the Multifunctional Composites Lab, and people are like, Eric, what does that mean? And I think, and when in my classroom, I always like to start with a definition, and I think, the multifunctional composites are really the simultaneous tailoring of both mechanical and physical properties to achieve new performance capabilities. And I think there's this tremendous drive to tailor materials that have active sensory adaptive energy storage capabilities. And and on the right here, this is from a recent paper that just applications in sensors and energies and actuators, and so this is really this multifunctionality. So this multifunctionality, in addition to when we talk about traditional fiber composites, we're usually talking about strength and stiffness, but now we can tailor this to integrate more functionality at the material level. These are just some examples of multifunctionality. In fact, this is from the AFOSR Mechanics of Multifunctional Materials and Microsystems website, which I've adapted a little bit, but I've highlighted a couple of the key words that I think are really both current and emerging areas of integrating multifunctionality in materials, specifically sensing, autonomic and reconfigurable systems, self-healing, self-cooling, energy management and generation, as well as actuation. So this is kind of I always refer to this as my signature slide, because I like to start with this, because this really gives you a sense of scale of what nanocarbon is relative to or mechanical reinforcement at the interface. So this is kind of one of the key challenges as well as the opportunity in nanomaterials. I think a lot of people, and I think many here, will likely be familiar with nanostructured carbon, but you know, I think the two most common things we talk about are carbon nanotubes and graphene. They have remarkable physical and mechanical properties, and I think also they're very high aspect ratio, you know, whether it's length per diameter or, you know, the length per the thickness of the graphene sheet. This has really stimulated, from a composites point of view, a lot of interest in the development of these composites. I come from a background, before I worked in nanomaterials and nanocomposites, I come back from a background of traditional fiber composites. And I think one of the things we talk about often in nanomaterials is we're going to make these from the bottom up, and that we're going to assemble them from the powders and fibers. And this is on the quote on the left-hand side. This was from over 20 years ago, this National Science and Technology Council Interagency Working Group. But from my point of view, this wasn't something new. Is that as a composite materials engineer by training, I knew that you select the materials, you tailor the interface, which is certainly at the nanoscale. You bend and twist the fibers together, you laminate them, and all the way up to the final net shape composite. So really, composites are bottom up manufacturing, and the integration of nanotubes is just one scale a little bit further down, or nanotubes or other types of nanoparticles or nano sheets. So this is what really got me into looking at the sensing aspect, was that when we dispersed, and this is carbon nanotubes, when we dispersed them in an insulating polymer, we saw very low electrical percolation thresholds. The polymer itself is insulating, and these are two different manufacturing techniques that we use. But certainly what you see is that even at just 0.1 weight percent, we see several orders of magnitude change in the volume resistivity of the material. And when I was doing these measurements, I had written some software, and I started bending and twisting the specimens, and I saw the resistance and the resistivity change quite remarkably. And so this is what we talk about in terms of once you're above electrical percolation, these nanocomposites become piezoresistive, in that when we strain them, the resistance changes more than we expect, simply based on a Poisson contraction and a change in length. So on the right here, this is some of the kind of initial tests probably we did on these materials. And you can see that with the stress strain curve from the strain gauge, we also see quite a significant resistance change. And I think the reason for this is you can think of all these discontinuous nanomaterials as these tiny little wires. And when you strain them, the tunneling gap changes between those individual wires. And then at some point, you know, I thought, in this point, I thought, well, obviously when you start getting cracks in the material, then you start severing some of those permanent connections. And this is a crack, and you can look down into the crack and you see the nanotubes protruding into the crack. And this is very small, about a micron, a micrometer across. And I think this is unique because really you need, in order to sense a microscale crack, you need a nanoscale wire. And when we first published this, it made a lot of press, but I think over the past several years, we've developed this technique, and we're now utilizing this and pushing it into applications. This was something emerging at the time, and now we're 14 years later, and we're actually utilizing these in applications. And of course, there's a lot of different things. It's really this electrical tunneling, you know, there's that contact resistance between the individual conductors that's added up over the network. And I think, you know, in this case, you know, it's just tunneling based sensing. So it's strain and cracking is what we're looking at. We've also done work with thermal expansion, measurement of polymer mobility. We published a paper where we could measure both curing as well as glass transition in situ. And it's also has some thermal resistive aspects as well that we can take advantage of. So we've done a lot of work in this area, and I won't go into all of this, but I think it's become a very rich area of research, and it's something that we're now transferring into applications. And these last two bullets here, the structural monitoring for repair of fatigue cracks and these textile sensors for garment-based monitoring is what I'll talk mostly about in the second part of the talk. So these are funded by the U.S. Federal Highway Administration, as well as the Department of Transportation, Delaware Department of Transportation. And then also we've looked at these textile sensors for garment-based monitoring, and that was funded by the National Institutes of Health, UNIDEL, and also the state of Delaware. So the first two things I want to talk about, as I mentioned, is the manufacturing approaches that we're using, because it's really the enabling technology, and then this, kind of initial work that we were doing, looking at sensing of cracks and how we extend that from sensing of cracks in materials to sensing of cracks in civil infrastructure. So the manufacturing approaches, there are two different approaches I like to think about. Is that one is dispersion and fusion, where you take whatever the particle or the nanotube or whatever it might be, disperse it, and then infuse that in to an array of fibers. And then the other approach is direct hybridization, where you actually combine the nanomaterials together with the fibers, followed by infusion. So these are just some sort of different approaches. I mentioned this dispersion into the resin. People have spent a lot of effort over the years looking at this, as well as myself, modifying the chemical functionality, looking at different ways to disperse it, such as calendaring approach, and then manufacturing the final composite using something like RTM or VARDM or maybe resin film infusion. The other approach is direct hybridization with fibers, is that basically integrating the nanomaterials together with the fibers, followed by infusion. And so there's a couple different ways we've done in my group, and there's other ways that other people have developed. But I think the three that are most common are chemical vapor deposition, dip coating and sizing, and something we spent a lot of time in my group over the past several years is electrophoretic deposition. So this dispersion and fusion approach, this is really where we disperse the nanotubes using some sort of a shear mixing. In this case, our work, we use a calendaring approach, and then we infuse the dispersion into the fiber. So this was many years ago. We're using vacuum-assisted RTM, or VARDM, as many people call it. And you can see the dark area is that dispersion of nanotubes in the epoxy resin. And one of the things we could see is once we manufactured the composites, we still had electrical percolation in the as-processed nanotube fiber composites. And because we had a very good dispersion, we didn't see any filtration. So here, this is just showing very similar to the nanocomposite, the electrical percolation. So we have the basically insulating vinyl ester and glass, and then when we add the nanotube to the matrix, we can significantly change the electrical properties, and that's really what enables our sensing approach. What's interesting is that they're also a little bit anisotropic, and it's partly because of the structure of the fibers, is that in the longitudinal direction, the percolating pathways go along the fibers, and in the transverse direction, they go around. The other approach is direct hybridization, and the first one that I talked about was CVD, and this is something I spent a lot of time doing in my PhD work. That's what you see, the nanotubes grown on the surface of the carbon fiber there. Basically what we do is we apply the catalyst, we heat treat the fibers, and then we put them in a CVD reactor, and we grow them under some sort of a hydrocarbon gas. And in this case, we used acetylene. And then, the catalyst we apply directly to the surface, and it takes about a half hour in order to grow. This is something that is a high temperature process, so it can be damaging to the carbon fibers, but is also not applicable to a lot of other types of fibers such as aramid or glass fibers, which may soften, or certainly you're going to burn off the sizing, which is a chemical coating on the surface of the fiber. Okay, so this is, what we call a sizing, or maybe a dip coating process, is that we create an aqueous nanotube dispersion, we dip it, and then we dry it. It's a fairly straightforward process. It's difficult to control, but I think what you see, you do see a pretty dense coating, and you can control that using the chemical functionality. You can control that, not only the volume fraction, but you can control the adhesion with the surface of the fibers. And we've used this quite a bit in our research as well. But one thing, and this is a unique process that we've really developed in my lab, was granted a few years ago a US patent specifically for depositing on and creating these unique films on non-conductive fibers. So this is what we call electrophoretic deposition. What we take is we take nanotubes, or we take other particles, we chemically functionalize them, and we disperse them in water. And that chemical functionality, by controlling the chemistry, they have a charge. And what that does is it stabilizes the dispersion. So you can think if we have two particles, if they have the same charge, they're going to repel each other. But then also, because we have charge, we can utilize those to move the particles. And again, of course, opposite charges attract. So here, if we apply a potential, they will deposit on the cathode. And in this case, what we do is we take a fabric and we back it onto the cathode, and utilize that to deposit. And one thing is, it's not just a physical deposition process, but it actually creates a very uniform coating. On the right-hand side, we've cross-sectioned a fiber, and what you see is this very uniform. On the top, this is actually a porous nanocomposite coating. We're functionalizing these nanotubes with a dendrimer called polyethylene amine that enables both the bonding, but also the dispersion, because that gives us the charge. And it's also something industrially scalable as a roll-to-roll process. One of my PhD students has recently developed a pilot line for making larger scale quantities. Right now we use it as a batch process. We also use water as a solvent, so it's more environmentally benign. And so this is when I'm talking, and I'm trying to explain why EPD is better than CVD, is that we have a lot of benefits, is that we have the control over the nanotube purity, we chemically functionalize it, we buy inexpensive multi-wall carbon nanotubes, and that critical step is that chemical functionalization. And these are just some examples of where we've deposited on some different fibers, and it doesn't just deposit on the fiber, but it completely surrounds each fiber in the bundle. So this is glass fiber, where you see a very uniform coating. We can also deposit on organic materials, such as wool, or things like aramid fibers, which would certainly disintegrate in a high temperature reactor. And we also have a lot of control over the thickness. These are a couple of cross-sectional micrographs of where we've deposited at varying thicknesses. And we have a lot of control over the processing conditions. We can do DC, or we can do alternating current, or AC. We use an unsymmetric waveform for this, but what you see here, these, particularly on the bottom, I think these are scanning gallium ion images, and the bright rings that you see are the conducting areas. Those are the nanotube network, and you see the very thin uniform coating on the surface of the fibers. And then over longer and longer time, we start filling in those gaps. And a lot of that depends on our processing conditions. So here, this is 10 minutes and 40 minutes, but we can control that also. So I think it's really not just raining down onto the fibers themselves, but actually this film grows over the fibers and around each fiber and is remarkably uniform. So that's really this enabling technology. And in these next ones, we use all the different techniques because they all can create conducting pathways. Sometimes different processes are better than others. But I just want to briefly mention and go through and talk about the nanocarbon networks for in situ sensing of deformation and damage. And this is really where we got into many years ago. It was really just me in the lab playing around and saying, well, hey, what if we make a fiber composite with these? Maybe we can use it to sense microcracks. And in my composites class, this is a classical mechanics problem, is that you generate these transverse microcracks in CROSS-PLY laminates, and then eventually, as you continue to strain it at higher and higher levels, you start getting a saturation of cracks due to shear lag. And of course, this matrix cracking doesn't necessarily change the Young's modulus that much, but it's certainly detrimental to durability. So this is an example. This is where I have a crack in a CROSS-PLY laminate. You know, the circles that you see here are the fibers that are going into the plane of the screen, and you can see the crack going across that layer. If we zoom in a little bit, you can see the individual fibers, and you can see it's debonded at the interface and cracked between the individual fibers. And now if we look in between the two fibers, we can see right at that edge, we can see the nanoparticles, in this case, the nanotubes sticking out. So we're creating those conducting pathways, and the cracks are breaking them. So this was pretty exciting that we could see this, but could we use this to detect damage? And we did these are the very initial experiments where we used, we looked at delamination, where we cut a center ply, and we could very clearly see the initiation and extension of delamination when we were loading this specimen in tension. And then we made a CROSS-PLY laminate. And this is also was very clear. At some point, you saw these jumps, and this was really that damage accumulation where you start getting transverse cracks, and then those transverse cracks start accumulating in the 90-degree ply, and then eventually lead to either interfacial delamination or fracture, fiber fracture, and then specimen fracture. So this was encouraging. So we did some more work where we were looking at if we loaded it in tension, those cracks would open. But then as we unloaded it, so that's the blue curve, that's the initial loading. But as we unloaded it, those cracks would close on it themselves. But when we reloaded it, those cracks would reopen and at a much, much lower displacement. So it was actually, the specimen was telling us, due to the piezo-resistive behavior and the opening and closing of cracks, it was telling us something about the state of damage. And this is really just, it shows the same thing. This is where we did progressive increasing cyclic loading, and at very low strain, you really don't see, it's like a strain gauge, but then at higher strains, you start seeing that deviation, and it becomes quite nonlinear. So I think what's interesting is we look at, we see the crack reopening, then we see that elastic loading, and then we go to higher and we see new damage. And this was exciting in that we thought, well, now we can use this to detect a lot of other types of damage and do that in situ. And this is just that same data that's plotted in a different way that shows you that damage accumulation, the crack closure, and the crack reopening. We did some very careful measurements. We call this the damage resistance because there's some permanent resistance change and also change due to the crack reopening. These are actually optical micrographs where we took edge replicas, we polished the side of the specimen and pulled it off so that we could count the number of cracks. Very tedious work. This was done about 9 years ago. But recently, another student, this was done where the nanotubes were dispersed, but earlier this year we published another paper where we used electrophoretic deposition with similar success. And I think the key here is that this line here is particularly is with the linear accumulation of cracks, or the accumulation of transverse microcracking, is that the significance is that it's linear and it's really ohms per crack. And we've also validated this with acoustic emission. So when we see acoustic activity, and we also see that resistance change, so we know that we're picking up damage. We've done fatigue testing, and again, you see that crack opening and closing, as well as the changes, and this is over 5,000 fatigue cycles. A colleague of mine has also done some modeling work in this area. We're looking at this creating of a nanotube network in situ, creating of a finite element mesh, and then looking at that damage initiation and the eventual coalescence into a transverse crack. And the results quantitatively are not the same, but qualitatively match very well. In particular, the linear elastic part, up until you start getting CROSS-PLY cracks and then those jumps. So that was exciting. So now we wanted to take this, this is what I want to spend the last half of the maybe 20 minutes or so talking about, is how we can utilize these composites for structural health monitoring. So we can take this outside of the lab and not only know that there's damage, but know where that damage is. So the first thing I want to talk is some of our work in localized and site-specific damage monitoring, specifically using a technique called electrical impedance tomography, or in our case, electrical resistance tomography. And then I'll highlight our work, our very recent work in repair and structural health monitoring of infrastructure, both concrete as well as steel bridges. And so this is a video I just wanted to show. This was just some that an undergraduate student had done many years ago, is that he made this panel and we tailored it and we integrated the carbon nanotube network in a patterned way. And what you can see, that's actually me pulling on it, and we'll let it replay again. I think it's, yeah, so you see where I push on it, you see in the background, then you see the curvature of the plate. And then also where I grab on the corner in the background, you also see that corner of the plate lift up on the screen. So that was something where we could say, well, we can use these as distributed sensors in a structure in order to not only measure cracks, but we can also measure the deformation. So of course, one of the things we want to know is not just that there is damage, but where is that damage? And this approach we use is electrical impedance tomography. And I won't spend a lot of time talking about the theory, but essentially what we're doing is we're measuring boundary voltage around the corners, and we're injecting a current. And then from that data, you simulate the domain, and then you solve the inverse problem, and you reconstruct a conductivity map. And so this was some of our initial experiments where we looked at, here's a panel that we manufactured, and then we just introduced different types of damage. And again, so the reconstructions were quite accurate. The damage location and the damage size was quite accurate based on this carbon nanotube composite. This is another case where we looked at, well, can we use it to detect cracks? And so what we did is we basically cut a crack into the patch. And again, we could detect the damage location within reason, although the damage size was expanded, and it's partly due to the slightly anisotropic nature of the composite. So this is just another example. We wanted to say, well, can we really sense this barely visible impact damage? And I think, what impact damage is, if you have, the example often used is if you have an aircraft wing and you drop a hammer on it, you can't see the damage, but is there damage there? And so what we did is we did some low velocity impact. We took our composite and we put it in our impact tower. In the photograph you see here, this is our composite laminate, and you see the electrodes all the way around the boundary. This is a little bit tedious to apply, but we can actually integrate this into a printed circuit board, and we have. And then we did progressive impact. We impacted it at 5 joules, and then 10 joules, and then 20 joules. And then we did, after each impact, we did the reconstruction. And I think clearly what you see is you see that location that damage has formed. And at this point, at the highest impact, you could see a little dent in the composite, but at the lower energy impacts, the composite looks fine. But here we're certainly picking up that matrix cracking that is occurring during the impact. Okay, so now I'd like to talk about this recent project. Well, it's not so recent, and it's been ongoing for over 5 years, where we do repair and structural health monitoring of infrastructure. And, I think one of the things that we often talk about, nanomaterials is we make small coupons and we go into the lab and we test them because it's difficult to make large scale structures. But one of the things that I did is I had a close friend and colleague, Thomas Schumacher. He was faculty here in civil engineering, and we decided to get together and see, well, can we really utilize this to detect damage in larger scale structures? And the first time we tested a part, there was this concrete beam that was, maybe a ½ meter long. And, we joked that it was the biggest test specimen I ever tested and the smallest one that he ever tested. So it's been a really fun collaboration. So we thought at the very beginning, well, can we utilize this and create a distributed patch in order to detect cracks in whatever it might be. In this case, this is a pre-stressed concrete bridge girder. And what happens is over time you get these shear cracks, and can we use these U-wraps to detect the damage? And I think one of the things that's often done is if you put a strain gauge on the specimen, if you're not really have a strain gauge that's sitting right on or very near the crack, you don't really pick up the action. In this case, we could really have a truly distributed sensor that would be able to detect those cracks. And I think these conventional sensing approach, they're really point or quasi-point measurements, and you need a large number of sensors. So we thought, well, this could be an opportunity because we've developed a manufacturing process where we could scale up, and we didn't just make, small test specimens or small panels to cut test specimens from, but we could make this material that was meters long. And by doing this direct deposition, either through a dip coating or electrophoretic deposition. So I won't talk too much about this, but this is one of the test specimens. This is a specimen. The span is I believe over 3 meters. The specimen itself is about 4 meters long. And one thing you see on the left-hand side, these are U-wraps or shear wraps that have fiber reinforcement with them that's intended to be a repair because this beam was pre-cracked, and this does not have enough shear reinforcement. So this was to repair, but also detect damage. And then over here, these are the sensor only. This is some work by my PhD student, Hongbo Dai. And we also, in addition to the shear beam, we had a similar beam as what you see here. This is a specimen. This is actually a beam that's flipped upside down. So we're applying a composite to the tensile side, and at the interface between the composite and the beam is a non-woven sensor made of carbon nanotubes. So these students, this is Sagar, Shafiq, and Hongbo. In addition to the concrete work, and what I'll spend most of the next few minutes talking about is we've been looking at steel cracks in fatigue cracks growing in steel. And in the United States, it's a major problem, is that the average age of most bridges is, I believe over 45 years. And a lot of these have fatigue cracks in them. And in fact, early fatigue, in terms of design, really didn't develop until about the 1970s. So one of the ways to do repair materials or rehabilitate infrastructure would be to take that infrastructure and then bond a composite to it. And the feedback that we got is that it's great, but you're covering up the cracks so that the bridge engineers can't go out and look at the cracks anymore. So this is where we thought, well, now we have this unique multifunctional composite sensor. Maybe we can utilize this to detect that growth of cracks underneath the composite repair. So this is, I guess, a little bit of background is that, you know, there's a lot of fatigue sensitive details. That's one of the major reasons for the deterioration of a lot of our infrastructure in the United States, specifically steel bridges. This is actually a fatigue crack in a girder that we actually went out and we did monitoring on. We did traditional monitoring. And what you see here, these dark areas, is where they drilled what we call a crack stop hole. And that blunts the crack's tip, and that also drills away some of the strain hardened steel out of the crack tap at the tip of the crack, rather. So these fracture critical bridges are a major challenge, and there's a lot of interest in that. This is actually intended to be a repair technique, but it's not always very effective. Here you can see they drilled a hole, and then that crack reinitiated. So then they drilled, a couple of years later, they drilled a bigger hole. So our idea was that we could take our nerve-like sensors. So this top picture that you see here is a sensor that has carbon nanotubes deposited onto the fibers. You can see the fibers are dark. That is the carbon nanotube coating. And this is bonded onto a steel substrate that has a fatigue crack in it. As you can see, as that crack has grown, that the sensor also fragments because we've designed the sensor to fragment. And what that does is that as we're measuring the electrical properties and that fatigue crack grows, that starts, again, just like on a different scale where we're looking at microcracking in the composite, here we're looking at cracking in the steel plate. We're severing those conducting pathways. And then I think there's an animation here. So what we do is we apply a very thin insulating layer, and then we apply our nanotube sensing layer, and then we apply a structural composite layer to also be a repair. We can use it with or without the structural composite. And then we apply our electrodes for sensing. This is actually a patch, and here we're doing impedance tomography, but we're not actually measuring, sorry, let me go back here. Well, you can see on the right-hand side, there's a lot of electrodes, but we're not using all those electrodes in this measurement here. But you can see on the computer screen that as we start loading the specimen, that is really, that electrical response is in real time with the specimen. So again, you see the specimen in the background is compact tension specimen, and then you see that initial loading, and then we can measure that cyclic loading. So the first step was to validate this in the laboratory. Is it going to work? So we generated several different test specimens. These are compact tension specimens. In fact, I have one here in my office, and they're really not that compact. But this is one of the fatigue specimens. This is where there's no composite repair, and so that would be like in the left-hand corner. The other one is where, they're drilling crack stop holes in the field. We also drilled a crack stop hole. The other cases where we applied a structural composite, and also where we applied a structural composite and also drilled a crack stop hole. And so these are the results of fatigue life. So this isn't showing any sensing results, but it shows that the repair can be very effective. The crack stop hole didn't really increase the fatigue life that much. Whereas when we applied one without a crack stop hole, we got a 380% increase in the fatigue life. That's quite significant. When we drilled a crack stop hole, we saw another, a higher, over 500% increase in the fatigue life. There were some practical applications, or there's some practical implications that this was difficult to do because of the crack stop hole. We would have adhesive rolling into the crack stop hole. Okay, so these are the specimen configurations. On the left-hand side, this is just the, this is figure A, right? So that is just our compact test specimen. You can see the fatigue crack right at where we machined the notch, and then we're just monitoring that until it fails. So here we've applied our composite repair and also integrated our, at the interface, also integrated our sensor. So we monitor the crack growth behavior. One of the things we do is we can measure the back face strain. And the back face strain tells us something about the crack length. So here you can see that so there are two cases where there's no repair, crack stop repair. They fail at about the same crack length. But here, where we apply the composite repair, we can drive that crack much longer than the critical crack length because we're taking stress off of the crack tip. One of the unique things, so I'm a material scientist. My PhD is in material science, so I like to look at fracture surfaces. So we looked and we could see the beach mark. So what we're doing is we're measuring and using that we can validate the back face strain with our just physical measurement of the marks on the surface of the specimen. And certainly here you see the resistance change of the specimen due to the nanotubes, and then the back face strain change, which measures our crack length. The number of cycles, you see it's very linear. And then actually once we hit 462,000, we actually started fatiguing the back face strain gauge. So it didn't really give us good data after that, but I think it's interesting that we were not fatiguing the resistance change. And these are just some, this shows that we're able to detect, and this is with the number of cycles, and it was quite repeatable. And these are a couple of different specimens for the composite repair. But what's more exciting is, so once we validate it into the lab, we're putting it on a bridge. And this is in Wilmington, Delaware. This is very close to the train station downtown Wilmington, Delaware. And what you see on the right-hand side, so here, this is the river that goes through downtown Wilmington. The train station is right here, and this is the main downtown area of Wilmington, Delaware. And you can see this bridge is actually a drawbridge because it's over the river. It's fairly low, and we actually did get chased off when the first day we went out. There's a very tall ship, and they came by and they chased us off the bridge, but this is us going to install the sensor and the repair. This is the crack. You can see some corrosion, but you can also see the fatigue crack that is initiated. And this was actually initiated at a previous repair. So we went and we designed an integrated sensor, and we have integrated, and we have two sensors on this bridge. We're also measuring temperature and humidity. This is all sent to us over the cellular network, and it's self-powered by a solar panel. And on the right-hand side, you see a video taken on my PhD student's phone showing the first few days that we had that sensor on the bridge. We've generated a lot of data, and we're currently digging through that. But this is our little data acquisition system that we built that has a 4G LTE sensor or a radio in it. Okay, so the last part I want to talk about for maybe about the next 10 minutes is this new area over the past probably 2 or 3 years that we've been working on multifunctional composites for smart garments. And actually the coating that is applied to the individual fibers that you saw earlier is not just the nanotubes or nanoparticles just sitting on the surface, but it's chemically bonded to the surface, but they're chemically bonded to each other. So it creates almost like a sponge-like porous nanocomposite film. So this motivation of this work was to utilize this and some of our collaborators who do rehabilitation. And on the left-hand side, they have these sensors and they're measuring human motion, and they're walking on treadmills and they're doing motion capture. And you can see that it can be very bulky, to wear. It takes a long time to put on, and you can really only utilize them in a laboratory setting. But what we can do is we can create these integrated sensors where we can put it on clothing for everyday monitoring. And we've also, in addition to, so this is just a fabric sensor where we've created these coatings on the fiber. And this is a miniaturized, semi-miniaturized data acquisition system that is wireless, so we can transmit that through either Bluetooth or Wi-Fi or over a cellular network if we wanted. And you can see that size relative to a credit card. So it's not large, and there's opportunity to further miniaturize it. And I think this is, you know, where we were talking to some of our physical therapy colleagues. Delaware is very well known for their physical therapy department. And this is on the left-hand side, that is my PhD student, recently graduated actually, Sagar, and he's walking on a double belt treadmill, and he's testing out the sensors. And I think one of the things in a laboratory for rehabilitation, this is not really possible. It's very expensive. Typical physical therapy clinics do not have this type of technology. But in this case, we're really integrating these directly into the garment. So what we're doing is right now is we're stitching them on, but it can be seamlessly integrated. And because this coating is, you know, this porous coating, even though the tubes themselves are stiff, this porous coating is soft, it's breathable, it's soft to the touch, it's breathable, and it results in really interesting sensors. So this is, we've developed a couple different sensors. One is a very thin and flexible pressure sensor, which has some remarkable properties. On the right-hand side, the video shows one of the undergraduate interns doing one of the first tests of the pressure sensor in a shoe. He's carrying the data acquisition. As you can see, it's not wireless, although he's not tethered to anything. On the left-hand side, this is the sensor. You can see how thin it is. These are actually the shoes I'm wearing today. And you can see I can just slip it right pretty seamlessly into this hole of the shoe. And what we can do is when we can put sensors in different areas of the shoe, and we can measure the ball and the heel of the reaction forces. The black line is what they often call the M curve. That's the curve that you get from that double belted treadmill, or instrumented treadmill that you were looking at. So it can't separate the reactions from the front and back of the foot, but here we can, and it's quite accurate. And what's remarkable about this is I often joke that this is touch to tons, so it works in the tactile range, and it certainly works in the body weight range, pretty large resistance change actually. But we also in the manufacturing lab, we drove over it with a forklift, and there was no damage to the specimen or no damage to the sensor. So it's quite remarkable dynamic sensing range. We've also done human subject testing and also calibrated the sensors in order to validate them. And now, in addition, we don't just have to measure people in the lab on a treadmill. We can measure people walking down the street on different terrains. On the left-hand side, that's walking up the stairs, and you can see that the reaction forces are quite different on the different parts of the foot. On the right-hand side, that's the same graph that you saw before. But we've also integrated these, in addition to the pressure sensors, we've also integrated these into knee sleeves and elbow sleeves. In this case, in the graph, what you can see is that you can see if we move your arm to 90 degrees, the resistance change is quite remarkable, over 3,000% resistance change. And even just 30 degrees, we're seeing nearly 1,000% change in the electrical resistance. And the first time I saw the data, I said, well, are you sure you didn't make sure that you didn't multiply by 100 twice? But no, they are really that sensitive. And that's what you see in the video on the right-hand side, a student wearing the sleeve and then just turning their arm at different angles. And you can see that in real time. This is just another example of, instead of a elbow sleeve, this is a knee sleeve where somebody is standing and sitting. And you also see that very large change in the resistance at about 90 degrees, about 3,000% change in the resistance. This is another thing where I think it just shows the sensitivity of the sensor. In the video, what you can see is that that sensor is on the forearm, and the student is making a fist, and just that slight motion is being picked up, as you can see in the change in electrical resistance. So it's fairly large. Also, we've made finger sleeves out of this as well, with the idea of making like a smart glove that is pretty seamless. We played around with a little bit of virtual reality. It's a little bit crude at this point, but what you can see is when we stretch the sensor, you can also see that motion of the arm. So I guess with that, I'll just make a quick summary and conclusions. Is that, I think we've developed these manufacturing techniques and to add this new functionality. And here I talked today about, just resistive or piezo-resistive type sensing, but there's a lot of opportunity where we integrate, different materials that impart different functionality. And I think this is just kind of this case study. So we've used it for composites, and we've used it to detect damage. That could be, we've done fatigue testing, and so it could be used for life prediction. We use these pressure sensors. They show remarkable dynamic sensing range. That's something that we didn't expect that it would be so remarkable and durable. And then the sensors, we've utilized them, as you saw, for human motion, and then also for structural health monitoring. And we've actually, like I said, I showed where we put it on a bridge here in Wilmington, Delaware, but we also have a sensor on a bridge in Portland, Oregon. Okay, so with that, I just want to acknowledge everyone who does all the work. So, in particular, Sagar, who has recently graduated, he is still a postdoc here at Delaware, and Dehan, Shafiq, Amit, Colleen, and also Hongbo, who was a PhD student and was later a postdoc. He's since gone back to his home in China, but he's looking for a faculty position. My collaborators in civil engineering, Professor Schumacher and McConnell. Jill Higginson is my friend and colleague, working on the biomechanics aspects, and then the processing. We have worked with Andrew Ryder in Australia, so I've had a lot of fortunate to have international collaboration, and certainly looking for more. So there's research funding, NSF, NIH, Inbury, FHWA, Unidel, and there's a couple others. You see their logos off to the side here. And then also, as we talk about, going from research to applications, atoms to applications. We recently founded this company. We received startup funding as well as some laboratory space. It's called MCET Technologies. And we moved into the lab. That's upper right-hand corner. That's my parents visiting about a year ago. They were the first people who actually got in the lab. And then you see the bridge on the bottom. So I was co-founded with my PhD student, Sagar. So with that, I'd be happy to take any questions. I think I hit it right on at about an hour. So.
Yes, perfect, just perfect. Thanks a lot for this brilliant talk and many new interesting things. I mean, I'm happy to have had you here with us. Well, I do have few questions, 5 from the audience here that I can see. Okay. And then I have a few of my own. But I think I'm going to start with one of my own, because I noticed that you use multi-scale as the term for this kind of composites, right? But there are also some other denominations, right? Hierarchical or hybrid. How do you feel about these different denominations?
Yeah, so the term hierarchical, so to me, multi-scale hybrid composite just means that you're combining reinforcement scales. It doesn't matter how you're doing it. I think I prefer the term multi-scale hybrid composite, and I use that to refer to any of the different types of structures. So certainly you know, when we grow the direct hybridization techniques is often what people call a hierarchical composite. But I'm not a big, I prefer the term multi-scale hybrid, but yeah, I mean, I think that there's opportunities in terms of all the different structures. We have a wide range of different properties that can be achieved. So, and it's really just, it's the manufacturing processes that I think enable that.
Okay, thank you. Well, I'm going to do one more before I do the audience question. We do have a lot of time, so up to, we still have like, it's only 5 p.m. now here. Well, I noticed that one of your first papers on TNT on fibers was in 2002, right? Well, what since then, what was expected to happen with carbon nanotubes that didn't happen or just didn't work? Basically, from what people were thinking in the beginning 20 years ago, what actually didn't work, and what are the perspectives now?
Sure, and I think if we go back, so I started working. It was actually almost exactly 20 years ago. It was November 2000 was the first time I ever grew nanotubes. But if we go back, I think at the very beginning, you know, I think what made people enthusiastic about carbon nanotubes was their extremely high Young's modulus, as well as their high predicted strengths. And so the Young's modulus estimated or sometimes measured, even, you know, at the beginning, people were measuring above a terapascal or 1,000 gigapascal. Yep. And, you know, I think that combined with the high aspect ratio. So, so this was sort of this kind of motivation, is that you have this small diameter reinforcement that's very high stiffness and strength. Mm-hmm. And I think also, you know, if you look like at an Ashby chart or something of carbon or of fibers, and in fact, in one of my papers, I created one of these charts. And, you know, for carbon fibers, there's always a trade-off between Young's modulus and strength. So the high strength or, you know, higher strength fibers such as IM7 or you know, mm-hmm. AS4 have typically intermediate moduli. And the high modulus pitch fibers, you can get pitch fibers that are pretty close to a terapascal, you know, certainly over 900 gigapascal, but they have much lower strength. So there's always this competition between Young's modulus and strength. So I think what excited people is that carbon nanotubes had both, is that you could achieve something that had a high Young's modulus and a high strength. Because they're nanoscale, you could, you know, they're easier to perhaps disperse. So you could disperse a small, maybe not easier to disperse, but you didn't have this high aspect ratio fiber that you were trying to mix in. You could mix in your tube, and it wouldn't be as difficult to mix it in. Of course, I know it's always been difficult to mix nanotubes in. So I think that the initial motivation was strength and stiffness. And my PhD work, I did mostly looking at the mechanical properties. And so this was really, you know, this was one of the first things I did as a PhD student, but it was actually more of a case study where we're looking at where we could put the nanotubes around and actually modify the shear strength at the fiber matrix interface. You know, I think also a lot of, you know, not every, just like every carbon fiber, not every carbon nanotube is, you know, made the same, right? Mm-hmm. There's defects, there's, if you have multiple walls, there's issues of load transfer. So they have an effective lower Young's modulus and effectively lower strength, particularly in multi-wall tubes, because you're transferring load, regardless of what it is, whether it's rebar or a carbon fiber or carbon nanotubes, you have to transfer that interface, transfer that shear at the interface. But I think what really kind of grew out of that and is that I did a lot of work in this area, and then we were looking at, electrical properties, thermal properties, and I think it's really is the multifunctionality aspect is that, I mean, we can and we have utilized where we do electrophoretic deposition, we see nice increases in the interfacial strength and fracture toughness and things like that when we combine them with fibers. And but we can also modify the electrical properties, and that's where I think this aspect of multifunctionality has really, with carbon nanotubes, you have these high aspect ratios. So even if you just mix in a small amount, less than 0.1 weight percent, you can take pretty much any polymer and make it maybe not a real good conductor, but make it conducting. And then it also adds this sensing functionality.
Okay. Now that you mentioned, what was the increase in interfacial strength that you got with coating with CNTs?
On this particular, where we did CVD or where we. I don't remember offhand, but it was fairly significant. I want to say it was around 30%. 30%. Okay. I'd have to actually go back and look at the paper or
it's okay.
My dissertation.
Just to have an idea.
But it wasn't so much, and I think, I think there's room for improvement. It wasn't so much like, growing these little, hairs or the fuzzy fibers, we called it. And it wasn't like trying to pulling a tree out of the ground with all the roots. It actually, what it did is that, so I did a quick model, and if you predict what the shear strength or the shear modulus increase should be, it was pretty consistent with what we would expect based on what the shear modulus in terms of changing that. We did fiber fragmentation, and that changed that fragment length. So it was really more of a stiffening of the interface than it was because these were bonded to the surface, but they weren't like super strongly bonded to the surface. But one of the things is more recently we've done the microdroplet test on where we deposited electrophoretically deposited, and the electrophoretically deposited material is chemically bonded to the surface of the fiber. So we validated that with a lot of XPS and model interface system. And so it's that chemical bonding at the fiber, which really makes it so nice for the smart garment, because those are extremely well bonded to the surface of the fiber.
Okay. Do you usually use single fiber fragmentation tests for interfacial adhesion, or do you use other tests as well?
Sorry, say again?
Do you usually use a single fiber fragmentation test for the interfacial adhesion, or use other tests as well?
Yeah, so I mean, I guess just in general here at the center, we do almost every interfacial test. So we've done fiber push out, we do microdroplet. Years ago, they did fiber pull out, which is really sort of microdroplet, but on a different level. And then also fiber fragmentation. I think fiber fragmentation is, I knew how to do fiber fragmentation, so that's why I did it. But fiber fragmentation is nice because you can do one specimen and you get a ton of fragments. Whereas a microdroplet test, you're lucky if you get maybe 15% that the bond in the proper way. Yeah, so there are pros and cons to each test, definitely.
All right, so I'm gonna skip to the audience questions here. So the first one is, what are the pros and cons of using CNTs versus graphene, and what are the suitable applications for each of them? I noticed that you only talk about carbon nanotubes, right? But graphene is on the verge now; it's more famous now. So how do you feel about graphene?
Yeah, so I mean, we've worked with both. I always consider graphene as kind of a new material we could play with and compare it to what we did in carbon nanotubes. And I think one of the things is that, well, there's a couple of things. So because graphene is a 2D shape, it's more difficult to get it inside of the, you have long aspect ratio in 2 dimensions. So as far as getting it into the fiber bundle, you have to really make those sheets smaller. And of course, when you make the sheets smaller, you're reducing the aspect ratio, and that's what you want. You want a good aspect ratio, right? So that's one thing. And, I think graphene, so when we do electrophoretic deposition, and this is sort of an interesting thing with the electrophoretic deposition process, because the mobility of the particle depends on the size of the particle. And when we're looking at the electrophoretic mobility, the larger ones they move slower. So what happens is that you get a distribution general. It doesn't have as high sensitivity in terms of piezoresistivity. Okay. And we haven't spent a lot of time looking at it, but I suspect it's because it depends on how these sheets contact each other, whereas the tubes really contact each other at like a single quantum tunneling point. So if you might have multiple contacts between the individual sheets, and that essentially shorts it out. That's just a hypothesis. We haven't really investigated that much, but I could say at similar volume weight fractions, you'll see that the nanotube sensors tend to be higher sensitivity. So.
Okay, so I have one question here from the audience about how scalable these CNT-based graphene sensors are in terms of production cost. How scalable they are?
In terms of the tubes themselves, or in terms of the process that we're using for deposition?
I think it means here if you're able to use perhaps in a real scale, actual scale.
Yeah. So I mean, I guess the point is that we buy I haven't grown nanotubes for years. We have purchased nanotubes commercially. And when I was a PhD student, and we bought some tubes, and they were $800 a gram. And now we can get this better tubes for less than $1 a gram. And for what we're doing in, with these composites, we're not using a lot of material. And that process is inherently the CVD process for growing carbon nanotubes, which is how most commercial, particularly multi-wall tubes, are made. The CVD process is inherently scalable. I think it's really, and there's companies still making them, and there's really finding the applications for them, but they're fairly inexpensive now. For the deposition process that we're using, the electrophoretic deposition process, is we created a pilot line to do that. And I mean, I anticipate that we could make a lot of that material, but when we just buy the commercially available tubes and we disperse them in water and chemically functionalize them, and then we do the deposition. But when you look at, let me see if I can. Yeah, so if we come down and to here, the amount of mass that you're putting on an individual fibers is almost trivial, because it's a very thin film. It's typically typically in the 200, maybe a little bit bigger. I mean, we can control the thickness, but typically what we do is it's a couple hundred nanometers, and it's porous, so it's open, so it's not even a dense amount of tubes. So when we deposit onto a specimen, it's really just the mass changes like a fraction of a milligram. So we're really using it in a small amount. And actually going back, and as if we look at like if we go to like this work where we're doing in situ sensing, right? So most of these that we did, we chose 0.5 weight percent. You know, so 0.5 weight percent, you know, by volume is about, you know, weight fraction, volume fraction is about 2% or 0.2%.
0.2.
And then, or maybe 0.3%. I take that back, it's 0.3%. But then if you say have a volume fraction of 50% fibers, which could certainly be higher, but you're looking at 0.15 volume percent. So it's very low.
Okay.
So we're utilizing it in a pretty efficient way. So if even if it were still expensive, which it really isn't, we're utilizing the material pretty efficiently for the sensors.
Okay.
I mean, I can tell you it costs a lot more to send students in the lab to make the sensors than the raw materials cost.
Okay, I got it. Okay, there's another question about the sensors. I mean, how's the repeatability of the sensor outputs? I mean, if you do another sensor, the output's the same, the level of output's the same?
Yeah, that's a very good question. And I can tell you it depends. It depends on the sensor. You know, I think if we look at the repeatability and sensitivity, part of the reason we chose 0.5%, and let's see if we can, yeah, so we're up here. So when we're at 0.5%, you know, so I think if you look at the, you know, electrical percolation curve, right? And the sensors are more sensitive as you approach percolation. So as you get closer and closer to the percolation threshold, you get higher sensitivity. And that's partly because there are fewer junctions. But as you move away, you get better repeatability because you have more conducting junctions. You know, they're maybe shorting each other out in the network, so you have lower sensitivity, but it's more repeatable. And actually, that's why in all of the in situ sensing work, we chose 0.5% for carbon nanotubes, 0.5 weight percent dispersed in the epoxy. And the reason we chose the 0.5 weight percent is that it gave us very good repeatability in terms of the sensor. And then also it didn't prohibitively, at that concentration, it didn't prohibitively increase the viscosity. I mean, it increased the viscosity, but it was still high. It's still low enough that we could do vacuum infusion.
Okay. 0.5% in terms of resin weight, right? 0.5%. 0.5% in terms of epoxy weight, right?
Say again?
0.5% related to the epoxy weight, right?
Yes, yeah, 0.5% in the epoxy.
Okay.
And then I guess to the other side of the spectrum, I mean, I guess for each of these sensors, there's always a little sensor-to-sensor repeatability. So, you know, when we're using it to calibrate strain, you know, say if we're using it in the garment or if we're using it in, you know, on the bridge, we have pre-strained the material in order to generate a calibration curve.
Okay.
And most of the composites are pretty linear. The garments are not as linear. So. Okay.
Now that you mentioned that, I mean, did you get any filtration issues happening in the RTM? Because
yes.
Yes.
So, like in this case, one of the things that we saw, and in fact, we published a paper on this, and this is actually this paper, one that was in Applied Physics Letters. So, because every time I would go to a program review, the same guy would ask the same question. And one of the things we never saw any visible, I mean, I guess the point is it depends on your level of dispersion. If you get a really good dispersion, there's no filtration. Okay. If you have a lot of agglomerates, those agglomerates actually filter out. If you're doing Vardum, they filter out in the PLY because those agglomerates can be fairly large. And sometimes we have issues, or we had issues with the dispersion because there was instability or when we were doing the chemical functionalization, it wasn't fully reacted. But so in this paper, in this Applied Physics Letters paper, I had a student, you know, because the person would always ask me, well, does it vary? And does it depend on the orientation of the flow?
Yes, of course.
And so I'm just like, okay, we're going to make a panel. And I had it 90 degrees and 0 degrees, and we did the infusion all at once. And then I had them section them and do electrical property measurements along the whole length. And for that one, the electrical property measurements and the orientation of fiber when you were infusing, it was all within scatter. So there was no spatial variation or orientation variation. The one thing that we did notice, actually, which we weren't expecting, and nobody had at least reported it at the time that I had seen, was that the volume resistivity was a bit anisotropic. And that's because actually, you know, Chunyu Lee, who's the third author, he did some modeling, and the whole thing is that along the fiber has a lower resistivity or higher electrical conductivity, because it's statistically more likely that the tubes are going to create spanning clusters. But in the transverse direction or the 90 degrees direction, the tubes have to go around the fibers, so it's a longer mean path, and there's less. It has to fit through the gaps, right? So the gaps, you know, there's a wider space between the fibers.
That's very interesting. I mean, there's one extra question here about how long does it take to coat CNTs into the fiber? The process of coating, how long it takes usually?
To process in which type of a process? So
yeah, it doesn't say it, just to coat CNTs into the fabric or on the fabric.
Oh, to coat onto the fabric. Yes. So like so say I'm assuming this is related to the electrophoretic deposition, and so the coating depends on a bunch of different parameters. It depends on our applied voltage. It depends on the concentration of tubes in the dispersion, and it depends on the thickness of our fabric. But in these, and actually, let me. No, I don't think that picture is in this presentation. But we can get a really uniform coating, and we can coat for the smart garment stuff in less than a minute, maybe a little bit more than a minute. We can get a really uniform coating on everything. And again, it depends on a lot of different parameters, but it's a pretty fast process. If you really want to get a ton of tubes inside of the fabric, and it depends on how dense that fabric is, then it can take quite a bit longer. But mostly what we're looking for interface modification. And what we really want is a uniformly coated structure as quickly as possible. But my PhD student Dahan, he is the expert in that area, so he'd be able to go into more depth.
Okay, I'm going to do one last one, I promise now. It's from the audience here. Well, is it feasible to incorporate CNTs within aeronautical CFRP components to online monitor cracks from impact loads?
So could you repeat the last part of that?
Is it feasible to incorporate CNTs within aeronautical parts from CFRP components for online monitoring of cracks?
Yeah. In fact, we've done that, and there's a couple different ways. And one way I didn't talk about, it depends. It's like if you're putting it on the fibers or if you're putting it in the resin, you basically have to make your own prepreg. And most most aeronautics or most aerospace applications are prepreg and autoclave, right?
Yes.
So you pretty much have to make the prepreg with the carbon nanotubes in it, which can be done. We have also used, and I have a few papers, that we published a couple of years ago, where actually what we were doing is I think I have that video here, yeah. So like here, this was one. So these are patterned into prepreg, but they're they're interleafed into the pre-preg. So basically,
Okay.
they're continuous sheets, or I mean, we can do it different ways. We can print. We can take a macroscopic sheet and deposit it. We can put it on a carrier fabric and put it in between. And we've done fatigue testing. We've done a lot of other testing. And this is just like this. Okay, so it's just like in this video here. So this was actually a demo panel that we made for an engineer's day at an aerospace company. We have Engineers Week here in the US. So we made this for our show and tell, you know, so that people could pull it around and bend it. But it certainly does detect damage. And of course, it's more sensitive to lamination than it is to microcracking, but it is sensitive to microcracking.
All right, that's brilliant. Well, thanks a lot, Erik, for such a brilliant seminar, and also for being kind to answer so many questions here. But now I think we're running out of time. So I thank you again for accepting this invitation and for giving us this very enlightening talk here. Okay, thank you.
Thank you for having me. So
thank you. Now I'm gonna pass to André. Thank you, André.
Thanks.
Okay. Thanks, Professor Sandro. Thank you very much, Professor Erik, for this brilliant presentation. And congrats for your innovating spirit. Oh. This is very inspiring for our audience, especially for the students. We need this. Right. More practical use of these things. Thank you very much.
Oh. Thank you, and you're certainly all welcome. I'm happy to be here, and always happy to talk about my work. So,
thank you.
Bom, pessoal, agradeço a presença de todos e já aproveito para convidar todos vocês para o nosso próximo seminário no dia 25 de novembro, que vai ser conduzido pelo Dr. Sal, da Universidade de Delft, da Holanda, e pelo Dr. Humberto, da Universidade de Aalto, da Finlândia, tá? A partir da segunda-feira a gente começa a fazer a divulgação e abrir espaço para a inscrição de vocês. Agradeço a todos, desejo um bom fim de tarde, fiquem bem, se cuidem, tchau, tchau.